Okay, welcome to this video for Material Science 410. We'll be discussing some of the characterization found in the polystyrene controlled polymerization lab number 5 for the spring 21 quarter. So this polydispersity and degree of polymerization as well as molecular weight will be determined by gel permeation chromatography, the topic of today's lecture. So, as far as the general characterization methods that can be used on polymers, we have to address various characteristics like molecular weight, composition, and chemical functional groups, as well as thermal properties. So we turn to gel permeation chromatography, also known as size exclusion chromatography, to address molecular weight or molar mass. And we'll see here that the guiding kind of factor that helps us determine molecular weight is the hydrodynamic volume. That is to say, the size of a free chain, including size due to solvent molecules within this volume that makes up the chain size. NMR, on the other hand, we have learned elsewhere that this is good for determining composition, and provided that the molecular weight of the polymer is not too high, that is to say less than approximately 5,000 molecular weight, we might be expected to see N groups that are chemically unique than any repeating units in the chain, and we could determine molecular weight by NMR. We also can turn to NMR to determine the relative stereochemistry or stereoregularity in polymers, and this is a separate topic to this lecture. As we mentioned, functional groups are the sets of architectures of certain atoms to make up a group that is common, can be found and detected by FTIR, an infrared vibrational technique. And thermal transitions such as melting and crystallization can be determined by a calorimetric technique called differential scanning calorimetry, DSC. And ultimately, knowing something about the degradation temperature is useful, and we would turn to thermogravimetric analysis, or TGA, for that. Ultimately, TGA determined degradation temperatures are obviously useful for knowing things like the limits of processing temperatures for certain fabrication procedures for polymer materials. So, while we've generally given you a view here of many of the different techniques that are used to characterize a polymer, there are more. So, please don't think this is a complete list, but do recognize that there are other ways to determine these characteristics and others. So, on the topic of molecular weight or molar mass, we know that this characteristic is very important for the physical and mechanical properties of a polymer. Let's turn to the example of polyethylene oxide, PEO, which is comprised of a repeating unit that contains an ethylene unit, CH2CH2, with an oxygen. So it is the ethylene oxide internalized in that repeating unit, and that makes the main body of the chain until N groups of alcohol are present. And if we consider the final OH on the leading repeat unit, we have an alcohol group there as well. Families of polyethylene oxide can exhibit different characteristics depending on molecular weight. Should the set of molecules present be less than 200 grams per mole, we can expect the property of the material to be a viscous liquid that is clear. If the molecular weight range of all the molecules present is actually between 200 and 2000, we start to see the material behaving like a waxy solid, similar to your candle wax. And then if we instead access a material that's got higher molecular weight, all molecules larger than 2,000 grams per mole, or 2,000 Daltons, we would instead observe that the material behaves like a crystalline solid reminiscent of other brittle type materials. So in that example, we saw that mechanical properties were clearly varying between liquid, wax-like, and brittle solids for polyethylene oxide, and this is a general situation for many polymers. So the general property plotted against the molecular weight is shown here, where we can see various properties trending uniquely against that molecular weight characteristic of the material. We'll start here by knowing that commercial polymers typically are bound by these arbitrary kind of limits, and so in a sense, commercial materials have more limited range in these properties, given that they have a lower and upper molecular weight limit to their profile. But outside of those commercial materials, more unique properties or even lower metrics for those same properties can be found. So considering, for example, tensile strength, you can see here that starts very, very low for low molecular weight materials and builds almost to a plateau level here for very, very high molecular weight materials. A similar trend is known for melt viscosity. It builds near exponentially in this regard. And so if one is looking to do melt phase processing, for example, in injection molding, knowing something about this trend is especially important in the material selection for the processing conditions and temperatures, etc. Impact strength of a material also goes similar in characteristics, if you want, for the trend, as we saw for tensile strength, building near logarithmically here with increasing molecular weight. And other properties not reflected on this graph, things like melt point, glass transition temperature, degree of crystallinity, strength, modulus, viscosity, morphology, all depend on molecular weight. Clearly, lots of reasons to understand this characteristic of a polymer sample. Okay, so in order to determine molecular weight, there are many different approaches, and they can be grouped into three main categories. There can be absolute methods, there can be relative methods, and there can be fractionation methods. So an absolute method has the ability to measure molecule by molecule the molar mass of a molecule within a range of a specimen. For example, mass spectroscopy techniques like matrix-assisted, laser, desorption, ionization, time of flight spectroscopy is capable of massing individual molecules to determine the absolute molecular weight to a lot of precision, a lot of decimal points. There are other properties that allow for absolute molecular weight determination, including osmometry, freeze point, boiling point studies for appropriately molecular weight sized samples. Like scattering techniques, highly dependent on morphology and center of mass of a molecule, can be used here to determine absolutely the molecular weight. Sedimentation, the rate at which a molecule is allowed to be gravitationally attracted to the bottom of a container. And ultracentrifugation also exploits that characteristic and can determine the molecular weight in an absolute sense. Relative methods rely on standards, and the molecular weight of a polymer of interest can be related to profiles for those standards. So that is to say the molecular weights determined are relative to standards, and thus the idea of a relative molecular weight. Viscosity is a property that lends to relative molecular weight distribution and molecular weight determination in this category. Fractionation method is the one we'll discuss in this lecture, and this can be thought of as molecular sieving, where we ask molecules to separate in time or through a medium based on their size. So this is also a relative method in a regard, although it can be rendered absolute depending on the calibration method applied. The logic applied within this video is going to speak more to a relative determination here. And so this is where we see size exclusion chromatography, or GPC as previously mentioned. Okay, so size exclusion chromatography. We knew we were going to have to separate molecules according to their size. So let's consider how this might work. What we're looking at left is a pipe filled with a packing material comprised primarily of spheres that are known to be porous and have either tunnels or nooks and crannies within them, cul-de-sacs if you will, that will allow molecules to either pass through or reside in those cul-de-sacs or pockets for a period of time. What we know is that large molecules will not be able to penetrate into any of the small pores, but instead would have to flow around them and through this column of packed material more quickly. Okay, so imagining a sample that contains both large, medium, and small molecular weight polymers, we can consider a simple thought exercise of how large molecules versus medium versus small molecules might pass through this pipe comprised of this porous packing material. Conversely, you might expect that small molecules would be able to diffuse in and out of small channels or cul-de-sacs or pockets in the packing material and would therefore reside longer on each packing particle before eluting out of the pipe. So to help this, we're going to set the solvent conditions very carefully, and the sample will be dissolved for this study, and solvent will be constantly pushing an injection volume of the sample already dissolved in that same solvent, and we'll be pushing that solvent through and monitoring the elution as solvent and macromolecules, polymers, come out of the pipe. So in that regard, we can see here the input to the pipe and the exit for the pipe. And ultimately, some sort of detector here would be able to register the presence of molecules by way of either a viscosity change momentarily in what was coming out of the pipe, perhaps a refractive index change, given the refractive index difference between molecules and the solvent used. Lots of ways to detect elution products through this pipe. If we think about the profile of how that detector would register the presence of molecules versus time, we might have the profile shown here. We can see here that the yellow population is eluting at the lowest amount of time, closest to the y-axis. So this would be what would be expected for the larger molecular weight molecules that are forced to just pass beside packing material and not associate with the internal pockets in that packing material. Smallest molecules can spend more time in those pockets and in channels or other nooks or crannies within it, and would here be displayed as the last elution product versus this time graph. And of course, medium would be somewhere in between, shown here. So in this regard, we are able to sieve the macromolecules according to size. We rely on their interaction with the porosity in the packing material. So this is overall is a very convenient method to evaluate molecular weight and molecular weight distributions of a polymer sample. In general, it's not absolute because we must use polymer standards that establish the profile for elution time for a certain polymer of certain size to elute from the column. So we relate molecular weight to that time of elution, and this is done with polymer standards that may not match the chemistry and the size of the exact polymer in question. And so, as said earlier, the separation is dependent on the hydrodynamic volume of the chain and not necessarily the true molecular weight. So, touching on hydrodynamic volume. Hydrodynamic volume is known to depend on the polymer structure and the solvent used. By choosing a different solvent, without changing the polymer's molecular weight, a different hydrodynamic volume can be had. So polymers, as a consequence, in solution will either be in an extended or coiled conformation depending on their compatibility with the solvent selected here, and their overall main chain structure and side chain implications. So flexible polymers tend to be very coiled, whereas stiff polymers with stiffening groups, more multiple bonding and or stronger intermolecular forces will be more extended. Having good solvent compatibility with the polymer can lead to a more extended structure, therefore. So we can imagine the overall hydrodynamic volume as some arbitrary sphere that contains the macromolecules shown in blue here, as well as all the solvent molecules, as I'll sketch here as S, that help solvate and keep the chain in an extended conformation. A different polymer, perhaps with more branching, more structure per repeat unit, can have the same hydrodynamic volume, but more macromolecular structure within it and less solvent to occupy that same volume. So here polymer A and B have the same hydrodynamic volume, but would have different properties. So here, the radius for hydrodynamic size for sample A would match the hydrodynamic radius of sample B, and properties like viscosity, the viscosity of A would be larger than the viscosity of B, given the opportunity for more extended chains and entanglement as chains like those at left bump and interact with one another. And the overall mass of sample A, as we noted, would be less given the more regular structure with little branch content versus the mass at right for sample B. So all that to say, polymers with the same molecular weight can have very different hydrodynamic volumes in solution, which here we've learned is the volume of a polymer rendered as a sphere, including the situation for the solvent to establish that sphere. And we've seen here in our diagram that hydrodynamic volume is related to hydrodynamic radius by the geometric calculation that you're familiar with. Here's a unique example to get you thinking about this. Here is a unique polymer. It looks a lot like polystyrene in its main chain. However, the side chain contains a unique ketone group positioned one bond away from another group called a cyano group. This functionality is called a keto group, and it can isomerize to a different version where no atoms are lost. There's simply a rearrangement. So the enol form of it moves a hydrogen from this position to this position at the same time generating a double bond between those functional group sites. Again, no atoms have been lost in this isomerization. The molecular weight of the chains would remain the same. But clearly, the change in the side chain programs for a change in the polarity at each repeat unit. The cyano group is very polar, as an example, and we might expect that to lead to different compatibility with the solvent of choice. So here in condition A, the condition where we have a keto form, this is more compatible with the solvent, and the chain is allowed to extend in a random coil to a larger extent and acquire a larger hydrodynamic radius or hydrodynamic volume. As the isomerization takes place and the hydrogen moves from the same spot where the cyano group is to form the alcohol group over to the left at each repeat unit, we can see that the compatibility with the solvent is not as good. The polymer would rather prefer to be in a more tightly compact coil, having more polymer-polymer contacts with itself and less solvent included in this volume. Here's an interesting example where molecular weight has not changed, but hydrodynamic size has, and you can see some of the consequences for measuring molecular weight, in that it's very specific to not only structure, but also the solvent chosen. Okay, more about that packing material in that pipe that we mentioned. What are used there are resins or cross-linked copolymers, typically, to establish the porosity needed to allow for size exclusion chromatography, or SEC. Here's the packing material is typically made from emulsion-type polymerization, where some agents are used to program for the porosity, and cross-linking can stabilize the ultimate structure that we inherit. So here you can see a bead, and clearly by SEM characterization, we see that there's lots of tunnels and cul-de-sacs and pockets available for macromolecules to interact with. So those hydrodynamic volumes that we saw just a moment ago with a chain inside would possibly interact with the pockets in one of these porous materials. The composition and porosity of these beads that are used to pack a column for size exclusion chromatography can be tuned, and the porosity can be very small, almost not recognizable here on the SEM, or the porosity can be tuned to be larger. And this is how one can dial the molecular weight characterization capacity of a column for column chromatography based on size exclusion. Okay, so in cross-section, here's a very simple diagram where, again, you would see those hydrodynamic volumes associated with chains not being able to interact with the pockets or tunnels in the material if they're large, but those that are smaller might be able to interact with some of the pockets in the material. Okay, and so again, as we've noted here, we're modeling dilute polymers as a hydrodynamic sphere in all these cases. What is some of the chemistry behind those resins that are used for the GPC or SEC columns? We mentioned that they're based on polymers, so here they can in fact be based on styrene themselves, which is the polymer in understudy in Lab 5 of Spring 21 Material Science 410 class. But crosslinking was needed to stabilize it. So in order to crosslink it, we install the same polymerizable group on the opposite end of the vinyl benzene, which is styrene. So styrene can also be described as vinyl benzene. And hopefully the terminology of divinyl benzene makes a lot more sense to you. Divinyl benzene acts as the crosslinker, and it will covalently stitch main chains together via that extra appendage for polymerization. So anytime there's a covalent link bridged by a phenyl group, we can point to a divinyl benzene monomer that's been used to establish that crosslink. These covalent bonds stabilize the ultimate structure of the bead, preventing full dissolution of the bead material in order to retain that in the pipe, in the column, and not elute or shed polymer material outside the exit of the chromatography pipe. There are various materials that are available. The one here is a styrogel comprised of divinyl benzene and styrene. One can actually use a version of that has sulfonate groups that are known and used as strongly acidic cation exchange resins. So the ionic and acid-base properties of the sulfonate group here can be exploited for that application. And the opposite application, a base anion exchange resin, can be programmed by putting ammonium groups with a fourth-fold substituted nitrogen in place to allow for that positive charge to be applied to the polymer, charge balanced by chloride in this case, whereas the former was charge balanced by that proton that's acidic. Some more of the hardware used on a GPC not only includes the columns, so a pipe, you can see some of those pipes shown here, and clearly there would be sort of an inlet in here, perhaps a connection between the outlet and the inlet of the next, and an overall exit out of the secondary column. So these columns can be in series with one another. But we'll need some solvents. So here you see some reservoir solvents, and this is what selects for the solvent of choice in the chromatography technique. Very important for establishing hydrodynamic radius or volume. There's going to be an injector, so that's typically robotically controlled by computer interface. And there'll be detectors, as we mentioned, which can be refractive index, viscosity, or light scattering based detectors. Those components kind of shown in a more system type diagram. You can see here the solvent is aspirated and used in the solvent delivery system, which feeds the injector as well as this sort of sample area. And together those allow for the sample and solvent to be placed and pushed into the GPC or SEC column. Solvent eluent, and when time lends to it, macromolecules would elute. Those would be detected by the IR or viscosity or light scattering detectors, and that signal would be processed into the chromatograms, such as time, signal versus time, as we mentioned. At this point, you might expect here that the flow rate of solvent can also allow for the x-axis to be plotted as volume of eluent to elute the material. So time and volume are synonymous by flow rate. That is, time can be converted into volume knowing the flow rate. So the x-axis in chromatograms is typically found also in volume of eluent, not only time for elution. Okay, so knowing that, we can now explain our x-axis in that regard. And in working with polymer standards, we can create our calibration curve. So that is what we're seeing at this point, is a calibration curve. To render the calibration curve linear, we plot the known molecular weight of the standards on a logarithmic scale, and this suggests that the logarithm of the molecular weight of the standards versus elution volume is a linear correlation. Very useful for calibration exercises when a later sample might elute at some time. We could measure that, and then we could track that back by equation or graphing to a y-coordinate, and then relate that y-coordinate to the molecular weight of a standard and report that as the molecular weight of the sample. So, in that thought process, if we're to use the calibration curve to determine a sample's molecular weight, we must select the same solvent for studying the sample as we've chosen to use for the standards. Very important. As you might expect, the polymer standards should be near ideal. Their molecular weight profile should be very monodisperse and low polydispersity. That is to say, all polymer chains in the standards should have very similar molecular weights. Similar molecular weights. And we'll see how molecular weight profile and the width of these curves can have a metric to describe that, a polydispersity index. Okay, so hopefully you see here that at short elution time, we would expect very large molecular weight standards to come out first. So these are going to be very large over here. And those that are smallest are going to be retained longer and take more solvent to push out of the column. So these are going to be the very small molecular weight specimen or standards, and everything in between. Peak positions would register the x-coordinate for the peaks here, and what's known for their molecular weight would be the y-coordinate. Okay, so here's a column that has been calibrated with polymer standards. You can see here the actual data and the correlation that is near linear. And so we have standards eluting from about 9.5 minutes all the way through to about 17 minutes almost. And the polynomial that fits this can be represented here, where rather than applying a simple linear calibration best fit curve here, which would be y equals cx plus d, we apply a polynomial with two additional terms here, the second order term and the third order term, to allow for a little bit of curvature in what is mostly a linear trend to push the bounds here outside the limits of our GPC elution column. So as you can see here, the curve with a polynomial is allowed to have a bit of curvature on the ends, and this allows us to push the application of the GPC column to further territory on the left and y-axis limits here. Okay, common kind of mathematical approach to opening up the availability here to use our column over a wider molecular weight range. Okay, mostly linear, so that is to say the coefficient on the term x here is going to be the dominant one. That on the second and third order terms are going to be minor, but still allowing for a little bit of curvature in the calibration curve. So that is to say third order polynomial fits are typical for calibration curves in the GPC technique. As we mentioned, a sample studied later with the exact same solvent might elute at a certain time. This would be matched against the polynomial, so we know the x-coordinate here. Input that into each x position, apply the same coefficients and exponents as necessary. This would determine our y-coordinate, which is, of course, our molecular weight that is on a log scale. So y is the log of the molecular weight. Okay, so what we know here about molecular weight and profiles of all synthetic polymers is that they have a mixture of differently sized molecules present. Okay, and so it only in rare cases, like in biology, can there exist one molecule for a polymer that is at the exact molecular weight known. Synthetic polymers have a mixture of these different size molecules. So in order to determine and report molecular weight, we use the number average and the weight average molecular weight according to the following formula. So the number average molecular weight is known as the sum of the number of molecules of mass I times that mass I. All that divided by the sum of the total number of molecules. Okay, this is probably the more easy one for you to rationalize. This is, for example, the number of students in a classroom at a certain mass as the first term, plus the next number of students at the next mass information times that mass, making up the numerator, all that divided through by the total number of students in the classroom. weight average molecular weight emphasizes the mass component there by simply squaring the mass information in that numerator and those set of terms, and introducing that as a first order value in the sum values here in the denominator. So this form of similar information allows for a weight emphasized contribution to the mathematics, and we get molecular weight information that is greater. MW in that regard is always greater than MN. Weight average molecular weight is always greater than MN. Okay, each can actually serve purpose past understanding the molecular weight profile. MN is typically responsible for colligative properties, things like how well molecules interact with one another, which of course depends on the number of molecules present and not necessarily their size. And things like viscosity and toughness are more dependent on the weight average of the sample in question. Polydispersity, or is abbreviated PDI, and this is known to be calculated by the ratio of MW over MN. And in that regard, polydispersity must always be greater than 1. And degree of polymerization we'll touch on at the end of this video. It has to do with the degree of polymerization, the number of repeat units. Okay, so here is a thought experiment to help you get a hold of number average and weight average molecular weight a little bit. Apologies, the sigma symbols here haven't presented themselves online here. Consider sample A, which is made up of 502 marbles, versus sample B, which almost has the same number of marbles, 500 instead. In sample A, almost all marbles, 500 of them, weigh 1 gram. And so the total mass there would be 500 grams from that subset in sample A. The remaining 2 marbles are very heavy at 250 grams instead, and that other population makes up an equal mass to submass for sample A. So the total mass here is, of course, 1 kilogram, and we see the same in sample B, 1 kilogram. For sample B, one subset of marbles is 400 marbles each at about 1 gram, and there is a significant population, almost as populated, here 100 this time, where these weigh sixfold that of the 1 gram, 6 grams total. Total mass contribution there, 600 and 400 for the former, totaling again to the 1 kilogram. When we consider the implications of using the number average calculation, we see here that the number average weight is 1.99 grams. When we do that on sample B, we're very close to that, 2 grams. So these two samples would be almost indistinguishable if we used mass information to 1 decimal point. When we turn instead to weight average information, now we learn that just how much range there is in the mass of the specimen. We see here that the weight average values really emphasize more the high-end subset in sample A. Weight average mass here is 125.5 grams versus a value of 4 for sample B. So clearly this shows some value in using 2 different metrics to report the profile of molecular weight distribution in a particular sample. Here's some actual data showing that. Again, we're on a log scale for the molecular weight. And here we see the molar mass plotted here. I'm sorry, logarithm of the population as the y-axis and the molecular weight as the x-axis. Here instead, MW values are going to be very close in this example. So we see here that the green data set has weight average molecular weight of 136,000 grams per mole, and the blue data set is not far off, 124,000 grams per mole. However, Mn is vastly different. Mn for the green set is close to that 136, 130,000. In the blue data set and sample, that is far lower at 57,000 grams per mole. We recall the polydispersity index was MW over Mn, and here you see a value of 1.04 for the much tighter molecular weight distribution profile, showing that 136 divided by 130 is the 1.04, versus the blue set of samples that is showing molecular weight profile that is very broad, reaching on the order of 10,000 molecular weight through to almost 1 million molecular weight. And that polydispersity index is well over double the value. Okay, so we've used some terminology here. Notice I've mentioned that the green molecular weight set is called a narrow distribution. So we can monitor and report parameters associated with the width of this peak according to polydispersity index. Okay, and I've used the term broad molecular weight for the blue data set here. That's a broad distribution, very different Mn and Mw values, and that PDI value was much larger as a consequence of the large difference between Mw and Mn. Okay, so as said, synthetic polymers are polydisperse, have a range of molecular weights, and we've emphasized PDI to help us understand that. PDI is a measurement of how wide the molecular weight profile is in a regard. So if it is monodisperse, we would have to have Mw equaling Mn to get a value of 1. And as we mentioned, only biopolymers, proteins in yourself, all have the exact same molecular weight because they're made very carefully through evolved biology inside you and me. So for very low polydispersity samples, like the former example on the previous slide, we can think about all polymer chains being very close in molecular weight to one another, but certainly if it's a synthetic sample, never will all molecules present be exactly the same molecular weight. Okay, so we describe narrow molecular weight distribution and equate that to PDI values that are on the order of 1.1 or lower. Moderate PDI has values for that metric between 1.1 and 2, and broad molecular weight distributions have the PDI values greater than 2. Additional terminology for gel permeation chromatography in chromatograms is to refer to the modality, how many modes are present. Okay. Ideally, the molecular weight would be Gaussian, so that is symmetric about the peak. However, this is quite uncommon given the conditions of synthesis and Gaussian distributions are hard to realize, but nonetheless, the terminology can be used as we walk a sample towards Gaussian with synthetic or controlled efforts there. Complex distributions can result where there's perhaps, a contribution of many different molecular weight profiles here, giving rise to the ultimate profile here. So this broad molecular weight distribution is also seen to have complexity and would be regarded as multimodal, meaning there are multiple peaks or shoulders present in the profile there. In a more simple case, we would have a bimodal molecular weight distribution where it appears that the profile only has two main populations present in that chromatogram. We mentioned degree of polymerization. So degree of polymerization refers to how many repeat units are present. So here 1, 2, 3, 4, 5, 6. Degree of polymerization of 6 with 2 N groups circled here as hydrogen atoms. And clearly we represent this as H, CH, CH3, CH2, H. When we put our parentheses, N refers to the degree of polymerization, and so to represent that longer molecule, we would put a 6 there. So the value that is subscript on our parentheses is the degree of polymerization. That can be calculated in two ways. We can have the number average degree of polymerization, which applies the number average molecular weight divided by the molar mass of the repeat unit. So this mass of repeat unit, everything in the parentheses, is M naught. Okay, we can also have the weight average degree of polymerization, which would apply the weight molecular weight average divided through by that molar mass of the monomer. Xn is synonymous with dPn, as well as Xm synonymous with dPn as well. Okay, for these calculations, as you've seen, we've largely ignored the mass contributions of N groups, given that most polymers have degrees of polymerization that are on the order of 20 or